Welcome back to the Deep Dive. If you've ever owned a 110 scale radio-controlled vehicle, well, you probably know the Tamiya 540 brush motor. Whether it's a touring car, buggy, truck, you know the one. The classic silver can, it's been the workhorse for ages.
Yeah.
Ubiquitous, feels pretty simple, reliable. But today we're diving deep into this motor. Not the windings or timing, though. We're zeroing in on just one tiny internal bit, the actual point of contact where the spinning part, the armature, meets the motor casing. Because believe it or not, that single interface, it dictates efficiency, how long the motor lasts, and yeah, its top speed.
That's exactly right. That's where the physics really hits the pavement, so to speak. If you're looking to unlock that hidden performance in what seems like a basic motor, the real aha moment, the key insight, is understanding the move away from sliding friction and towards, well, precision rolling friction. That transition is everything.
Okay, so this deep dive is really about finding a shortcut to, well, pretty serious performance gains just by tackling this one component.
Exactly. We're talking about reducing the most fundamental resistance that's just built into the system.
Getting rid of the drag, essentially.
Precisely. We're going after the single biggest source of parasitic drag inside a brushed motor. I mean, if the motor doesn't have to fight itself just to spin, then all that electrical energy can go into making the car move forward.
All right, let's really unpack the mechanics here, the actual physics of this friction. So, if I grab standard 540 motor, straight out of a new kit, what am I actually looking at inside? What supports the shaft?
Okay, so the standard setup uses what we call bushings. They're basically simple, solid sleeves. Typically, they're made from this porous bronze alloy. Sometimes it's called Oilite because it holds oil. The basic idea is the hardened steel armature shaft just slides directly against the inside surface of that softer bronze sleeve.
And when you say sliding,
Yeah.
we're talking metal-on-metal friction,
Yeah.
right? Even if there's some oil in there.
Yeah, fundamentally, yes. Even with lubrication. These Oilite bushings, they kind of rely on capillary action, drawing tiny bits of lubricant to the surface as things heat up, which is, okay for moderate speeds, but under the kind of RPMs and heat you get from a decent 540 motor, especially a tuned one, that oil film can break down pretty easily. Then you get actual metal-on-metal contact. And that generates significant heat, major resistance. It's actively working against the motor's power. It literally acts like a constant tiny brake inside the motor itself.
So we're not just losing potential speed, we're basically generating waste heat, cooking the motor from the inside out. Okay, so how does the upgrade, the ball bearing, fix this, like fundamentally?
Right. The ball bearing, or ball race as some call it, it's a completely different beast. A real leap in mechanical engineering, honestly. It's this complex, high-precision assembly. You've got an inner ring, or race, that's fixed onto the spinning shaft, and then an outer race that's fixed into the motor end bell or can. And sandwiched between them, you've got these little precision-ground steel balls held in a cage.
Okay, I get the structure,
Yep.
but explain, the magic. Why is that so much better?
The magic is the conversion of friction type. With the bushing, you have this relatively large surface area of the shaft dragging against the inside of the sleeve. That's sliding friction. High contact area. With the ball bearing, that huge contact area gets reduced to, well, almost nothing. Just these minuscule points where the balls touch the inner and outer races. They roll instead of sliding or dragging.
Ah, okay, point contact instead of surface contact.
Exactly. And converting that high contact sliding system to this incredibly low contact rolling system, that's the absolute basis for all the performance gains we're going to talk about. It just dramatically lowers the energy needed to keep things spinning.
Right, that makes sense. Which leads us straight to the big practical question. Can my motor, the one I have, actually be upgraded? Because if you look at Tamiya's whole 540 range, it's actually kind of complex. You've got your basic ones, your tuned ones.
It really is. And, the first surprising thing, when you really look into it, virtually none of Tamiya's 540 motors actually come with ball bearings installed from the factory. Almost all of them start with bushings. So the key to whether you can upgrade, it really comes down to how the motor is physically put together.
How it's built.
Yeah, there are basically two main types you need to be able to spot. First, you've got the sealed can workhorses. These are the ones where the end bell, the plastic cap at the end where the wires connect, is crimped onto the main steel can. There are no screws holding it on. It's meant to be permanent.
Okay, yeah, those are the super common ones, right? The standard silver can, maybe the 540J, pushing, 14,500 RPM, or the black sport tuned, which is a bit faster, maybe 18,300 RPM. They're reliable workhorses, but if they've got bushings,
They're stuck with them,
yeah.
exactly, because you can't take them apart without basically destroying the can or the end bell. So those internal bushings, they're in there for good. Solid entry-level power, sure, but they definitely hit a performance ceiling because of that internal friction.
But wait, the sources mentioned something interesting there. Tamiya often says that if you install one of their faster-tuned motors, like the Sport-tuned, you must upgrade the chassis to full ball bearings. Why push the chassis upgrade so hard if the motor itself still has bushings?
That's a really crucial point. It shows they understand the issue. See, if you ramp up the rotational speed inside the motor significantly, you amplify friction losses everywhere down the line. In the gearbox, the axles, the drive shafts. If the rest of the car is still running on cheap plastic or even metal bushings, the higher speed just generates so much extra drag and heat throughout the whole drivetrain that it can actually cancel out the gains from the faster motor.
Wow. Okay.
So to me is basically acknowledging indirectly that even their sealed tuned motors create significant friction. They're telling you, look, this motor spins fast, you better remove friction everywhere else just to feel the benefit.
So friction really does compound through the whole system. Okay, that makes sense. Now let's get to the good stuff, the motors that can be upgraded, the tunable powerhouses.
Right, these are typically your higher end competition focused motors. And the dead giveaway. Look at the end bell. If you see two small screws holding that plastic end bell onto the metal can, bingo. That tells you the motor is designed to be fully disassembled. You can clean it, replace the brushes when they wear out, adjust timing sometimes, and crucially for us today, you can physically remove the stock bushings and press in ball bearings.
And this category includes motors like the Superstock RZ, the High Torque TZ, the Off-Road BZ. But we're talking motors pushing well over 26,000 RPM, sometimes close to 30,000. But here's the part that still gets me. Tamiya sells these premium, expensive motors designed for peak performance.
Yeah.
And they still put bushings in them from the factory. Why on earth would they do that?
It seems crazy now, right? But it's almost purely down to racing history and maybe a bit of cost management back in the day. These motors were developed during the peak era of stock class racing. And in many racing leagues back then, the rules strictly mandated that you had to run the motor exactly as it came out of the box. No modifications allowed.
Ah, so stock meant stock. Bushings and all.
Exactly. So by supplying them with durable, cheap bushings, Tamiya met those stock class rules and kept the initial purchase price a bit lower, more competitive. The ball bearings were then sold separately as the obvious, essential hop-up part.
So it was like a deliberate two-tier system. Design a brilliant motor, then intentionally hobble it slightly with a dollar's worth of bushings?
Pretty much. They knew the potential was there, but the rules and market kind of forced this approach. The bearing became the key to unlocking that potential.
Okay, that historical context is actually really important. So let's say you've got one of these tunable motors like a Superstock RZ or TZ, and you're ready to do this upgrade. What exactly do you need to buy? Are there loads of different sizes?
Thankfully, no. This is one area in RC that's remarkably standardized, at least for these 540 motors. You need two bearings, one for each end of the armature shaft, and the size code you're looking for is almost universally R2 sys.
R2 systems. Okay, like the secret code?
Kind of, yeah. That's the code you'll search for. If you want the actual dimensions, let me see. It's 18-inch inner diameter, 38-inch outer diameter, and 532-inch width. That 18-inch inner diameter is the standard shaft size for pretty much all 540 motors.
Got it. Now let's talk about that ZZ part in R2 Fizzies. Because bearings often come with metal shields, the ZZ ones, or with rubber seals, usually called 2RS. You're saying ZZ is crucial here. Why would using the wrong type, say a rubber sealed 2RS bearing, be such a bad idea inside the motor?
Oh, it's a huge mistake. It completely undermines the whole point of the upgrade. See, those 2RS rubber seals are fantastic for keeping out really fine dust and water, great for wheel axles, drive shafts, things exposed to the elements. But, and this is the critical part, those rubber seals make physical contact with the spinning inner race of the bearing. They rub against it.
Ah, so they create their own friction.
Drag. Exactly. They generate significant drag. If you put 2RS bearings inside your motor, you might honestly be better off just keeping the original bronze bushings. You've just swapped one kind of friction for another. You've added a brake right where you wanted things to spin freely.
Right, defeating the entire purpose.
Totally. The ZZ means the bearing has non-contact metal shields. These shields sit extremely close to the inner race, creating a kind of labyrinth path that helps block larger debris, but they don't actually touch. So they add virtually zero friction.
And since the motor can itself provide some protection.
Precisely. The motor housing does most of the protecting. So for maximum RPM, maximum efficiency inside the motor, ZZ is absolutely mandatory.
Okay, that distinction alone is super valuable. Now, quickly on materials. We mostly see chrome steel bearings, but then there are ceramic hybrid ones. Are ceramics worth the extra cost?
Good question. For, I'd say 99% of users, standard chrome steel bearings are the way to go. They offer a massive, immediately noticeable improvement over bushings. They're durable, reliable, and give you the absolute best bang for your buck. Perfect for everyone from casual bashers up to serious club racers.
So, a huge step up already.
A huge step up. Now, ceramic hybrid bearings, these usually use steel races but have ceramic balls, often silicon nitride. They are technically better, they're lighter, harder, rounder, generate slightly less friction, but the performance gain is marginal, maybe 1 or 2% more speed or efficiency in perfect conditions, and they cost significantly more, they can be more brittle, and they often require much more careful, specialized cleaning and lubrication.
So, really only for the elite competitors chasing fractions of a second.
Exactly. If you're at the absolute top level of competition, maybe. For everyone else, stick with good quality chrome steel R2 Elysees. It's the smart choice.
Okay, so we've got our tunable motor. We maybe cleaned it up a bit, popped out the old bushings, carefully pressed in our shiny new chrome steel R2 Azeri bearings. What's the actual difference? When I pull the trigger on the transmitter, what am I going to feel? What's the real-world impact?
It really feels like the car just woke up.
Right.
Seriously. What you're experiencing is the direct result of slashing that internal friction, all that electrical energy that was being wasted as heat before. Now it's going into making the motor spin faster and more efficiently. You get three main payoffs. First, efficiency and runtime. Because there's less drag, the motor needs less electrical current from the battery to hit a certain RPM, or it can hit a higher RPM for the same current. Meaning you get noticeably longer run times on the same battery pack,
Yeah.
often, several extra minutes of driving or racing, which is huge.
Okay, more time playing. That's always good. And second payoff is presumably speed.
Oh, yeah. Speed and RPM. Less resistance means the armature can just spin faster for the same voltage you feed it. It's hard to isolate just the motor bearing swap easily, but remember that chassis bearing test data.
Right, swapping chassis bushings for bearings give a 12.7% RPM increase at the wheels.
Exactly. And since the motor shaft spins way faster than the wheels and is arguably the primary friction point we're fixing here, the percentage gain inside the motor itself is often even more significant. You get more top-end, faster acceleration. It feels punchier.
More speed, more punch, longer runtime. Okay, what's the third payoff?
This one might be the most valuable, especially for the average person who doesn't want to be buying expensive motors all the time. Longer motor life.
Oh, because of the heat reduction?
Precisely. Heat is the absolute enemy of brushed motors. Excessive heat demagnetizes the magnets in the can over time, making the motor weaker. It burns up the brushes faster. It causes more wear and tear on the commutator segments. By running significantly cooler, which ball bearings allow the motor to do, you are dramatically extending the service life of that motor, especially important for those pricier superstock motors.
So spending maybe, $10 on a pair of bearings today could save me from having to replace a $50 or $60 motor prematurely down the road?
Absolutely. The return on investment there is enormous, purely from a longevity standpoint. Never mind the performance gains.
And I guess it feels better too. Consistency.
Yeah, that's the other part of drivability. You get a crisper, more immediate throttle response. Bushings can feel a bit sticky initially, and their friction changes as they wear and heat up during a run. Ball bearings are just smooth and consistent, lap after lap, run after run.
Okay, the verdict seems crystal clear then. Upgrading a compatible Tamiya 540 motor, one with the screw-on end bell, to Arcumenzi ball bearings isn't just an upgrade. It sounds like maybe the single most impactful, cost-effective performance boost you can make.
I definitely agree with that. It improves pretty much every aspect of how that motor performs. It's mandatory if you're club racing with one of these motors, and honestly, highly recommended for anyone using a tunable motor who just wants it to last longer and run at its best.
This whole deep dive was fascinating because, as you said, the source material really pointed to this deliberate engineering choice driven by old racing rules. These high-performance motors were basically shipped with a built-in handicap, these cheap bushings, creating this hidden layer of performance just waiting there.
It really was. And that makes you think, doesn't it? It raises a bigger question for you, the listener. to ponder. This specific example shows how some legacy constraint, or maybe just a tiny cost-saving measure, can introduce significant friction and inefficiency into what's otherwise a well-engineered product. So where else in your everyday life, maybe power tools, kitchen gadgets, even the software you use professionally, might there be simple low-cost components holding things back because of history or budget? And what hidden potential, what latent power could you unlock if you looked past the default and sought out the superior engineered alternative?
That's a fantastic thought to leave everyone with. Find the hidden bushings in your life. We'll catch you next time for another deep dive.